Okay, so welcome to the class again. So great. So reminder for video recording. So recording is, I hope, running. Yes, it's running. And yeah, thanks for submitting the exercise 1. It's all being graded now. And so far, there's no tutorial after the lecture today, but feel free to ask questions afterwards, okay? You can always do that. And then I'll jump into the content of the attributions, explainable machine learning. So in this lecture, so last lecture, we talked about what we really need from the explainability of machine learning. But now, today, we're going to talk about actual methods for extracting explanations from neural networks. It's called attribution. And I'm going to explain what I mean by attribution to test features. So let's say you have a trained model first, and then you're giving an input image. And of course, if you pass it through the network, and then eventually you're going to get some kind of class, which is answering the question of what is the content of the image. But for example, this is a CAM method, class activation mapping. And as a result of doing class activation mapping, you're going to get an answer to why model, why do you think this is a cat? So an explanation is a function that takes an input image as an input, and also the class of interest is as an input, and then the output is some sort of explanation of which pixels or which features contributes most to the decision that this is a cat. So I talked about features now, right? So I try to generalize the notion of pixel or feature to any kind of aggregation of inputs to a model. So for example, for visual models, it takes an image as an input. So naturally, every single pixel can be thought of as a feature, but you can sort of aggregate your pixels into an image patch, and you can also think of each patch of your image as a feature that's input to the network. You can also think of superpixel as a feature, or entire instance mask per instance as a feature. Okay, and then think about which feature is contributing most. Okay. Or if you go a little high level, then just visual domain, you also have those attributes like cute, 90%, furry, 40%. They could be subjective, or they could be pointing to specific regions of the image, or could be kind of like describing the general feeling of the image and so on. And then from there, we can try to figure out how much each attribute is contributing to the decision that this is a cat. Okay, so feature is a very general concept. For language models, you're taking a token sequence as inputs to the model. So in that case, you can think of the contribution of each token or each word towards the final decision. Okay, so for natural language domain, people are doing attributions to words to analyze them. Now, last time we said counterfactual reasoning matters a lot for explaining to humans when we explain to each other. So let's see what is the most basic way to explain a decision of a model in a counterfactual way. So one way we can do is to remove certain set of pixels from your image and see if the prediction is still cat. Okay. So if this feature is missing, is this image still going to be predicted as cat? Okay. And then there are some follow-up questions. What do we exactly mean by missing? Do we mean just removing some pixels and then filling them in by gray pixels or black pixels or pink pixels that you're probably never going to see in natural images? Or do you probably wish to in-paint those pixels by inferring from the surrounding pixels? Okay. So even for this simple question of removing a small square and replacing that with missing pixels, encoding some missingness, is raising a lot of questions. You can also do this, right? Who prevents you from doing this? And this is still a counterfactual question. What happens if you do something else than now, and what happens, right? Is that still going to be predicted as a cat? And as a result, what's the response for the model? Is it now predicted as a cat or a dog? What does that tell us? So coming back to the intrinsically interpretable models, such as sparse linear model or decision trees, we know that those models support this kind of counterfactual analysis. Because, for example, these VIs are features, and we know what's going to happen to X when you remove one of the VIs, right? Because, yeah, it's just a summation, right? So every feature is contributing linearly to the final output. So we have a very good understanding of what's the expected output and what is the mechanical kind of relationship between the features and the outputs. It's very good. So actually, one implicit aim that's running through a lot of explanation methods is turning some part of the model into a linear model. Okay, so that's kind of the common mindset for these attribution methods. But doing this kind of counterfactual, sorry, yeah.
How does counterfactual reasoning look like for the tree, the decision tree?
Well, you can just choose the other decision. Yeah. So in other words, you can kind of do the full simulation with this model in a very human understandable way, right? Whereas for neural network, when you change something in the lower layer, it's highly unclear which pathway you're going to take to the final answer. So, yeah. For neural networks, doing this kind of so in this case, what you can do is you can do this kind of reasoning for every pixel in the image or every sliding window of the image, right? By running your sliding window of missing pixels from left to right and then from top to bottom. But that's going to take a super huge amount of time. You have to consider the number of sliding windows in the image. And for every missing window, you need to consider different ways of altering the content. And of course, you're not doing this for a single image probably, and you'll probably do this maybe on the fly, real time, or for the whole data set, actually. And that takes like months and probably years. But we're going to start with a very special case where we can actually compute this counterfactual very quickly, which is when the feature is pixel and the perturbation is very small. So let's say the original pixel value here is like this, and these are RGB values. And we are perturbing the R value by 1 of 255. And then let's say the CAT score has decreased from 96.5 to 96.4. That's a very small perturbation. But probably this sounds familiar because that's exactly how you compute the gradient numerically. So the dumb way to compute this kind of perturbation is just do the forward pass, the number of pixels times 2, because you wish to compute the original one, and then the results after perturbing the pixel a small amount. And that's a dumb way of doing that. But the smart way of doing that is just do one backward pass through the image, through the network onto the image. And that's going to give you exactly the estimation of what's going to happen to your output when you change every pixel in a small amount. Okay. So another way to think about this is your backpropagation is linearizing the whole model around the test sample, right? Because the gradient is basically the tangent plane of your function in the space. And so, and this tangent plane kind of guarantees that your function output with this linearized solution will be the same around the input of interest. So this is called local explanation, right? You only care about explaining around this single test input. And you can say you're introducing some sort of linear surrogate model instead of the original function, because now you're only looking at the linearized model on top of this model. Yeah, so here comes the what I said before, right? So this is in a way trying to linearize your model in some way, okay? And this is the result of your input gradient. It's called saliency map. I don't like this this terminology because saliency is, sorry, it says sensitivity as well. Okay, so a lot of different names are attached to this input gradient. I personally prefer to just call this input gradient rather than sensitivity map or salience map or anything else for the sake of clarity. But yeah, and here what you can see is maybe the class was this deer or what is it called? Gazelle? Yeah. And yeah, they should have actually told us which class was being predicted here, because the class could have been the savanna or the field. But anyways, the sensitivity map seems to indicate this animal region as a sensitive region for the prediction. Not sure if that's really helpful or not, but yeah. So if you keep looking at those input gradients, you're going to be wondering what do I actually get out of this, right? Because you're going to see a lot of noises, and you don't actually see you don't even see the object in those kind of input gradients maps, right? By the way you visualize those input gradients is by taking the max across the three channels RGB, because otherwise you're going to get a heat map with three colors, R, G, and B. But ideally, you wish to kind of look at the pixel-wise contribution to the prediction. So there needs to be some kind of reduction of the color channel dimension. So in this case, you're taking the max. And some people also take the absolute value to make sure that even the negative contributions are considered contributions, okay? But still, they are very noisy. So what people tried was to get a smoother estimate of the contributions. So what they do is they perturb the input, and then based on those perturbed inputs, you get the input gradient, and then average them, okay? So given input x, you do the perturbation, epsilon, and then take the gradient around this x plus epsilon, and then average them across the different noises that you put on the image. And that gives you a slightly better estimate, because I guess the input gradient is super noisy as well. And so by combining different perturbations of the gradient, you can reduce the noise and finally see the relevant part of the image. Okay, yes?
The idea here is that the noise cancels out because average was
yeah. Yeah, the idea is that probably the signal stays there and the noise is kind of fluctuating. And so you can kill them out. So conceptually it looks like this. So this is the gradient idea. So there's an input image, and the gradient is kind of measuring the response to perturbation in the I pixel direction. So you can kind of do the Taylor expansion around f of x plus delta ei, which is a small perturbation of pixel I, and see the change in the response. And that's given by this small perturbation amount delta times the input gradient around pixel I. And now what this smooth grad is trying to do is something like this. You first perturb x into different local variations of x around it according to normal distribution. And then for every perturbed point, you further perturb uniformly into the ith direction, and then see the average response of those changes in different perturbed inputs. Okay, so this is given by this expectation over responses, which is again approximated using Taylor expansion or gradient computation according to this expectation, which is taken out now, and then the gradient into the direction of I. And this is given by, this formula. So you take the gradients multiple times and then average them. And that gives you smooth grad. And it kind of expands your originally very local computation of the gradient to a slightly more global regions around X, okay? So now we are trying to go from local approximation of your function to more and more global. So here we went a little bit more global, and now we are going very far into the global input space. So instead of just perturbing around a single point, we are actually interpolating between 2 points in the input space along a straight line. So you're kind of, this is a pixel space, so you're kind of interpolating between, let's say, an image and a black image by kind of slowly dimming your image into a complete black image, okay? And you do the same kind of gradient computation at every intermediate point along the curve, straight line, and then average them afterwards. And that's going to give you something called integrated gradients, okay? And that is given in the same way. So here you're taking the expectation over alpha, which is parameterizing between 0 and 1. So when it's 0, then your input will be x, and when it's 1, your input will be x prime, x, and then this is estimated by taking the gradient here, right? And then you can of course swap the expectation with gradient, expectation with the dot product, of course, because both of them are linear. And here you can actually estimate the expectation here by it's not an approximation, it's the same thing, right? Because alpha is a uniform distribution. So you're taking the gradient here, and then you're basically sampling alpha from 0 and 1. And that gives you this kind of estimate of your pixel-wise contribution. But this is not exactly called integrated gradients yet. So the left term here is what I just derived. But what integrated gradients really compute is something that is written on the right. So you're actually multiplying this x prime minus x times this integrated sum of gradients. So now I was actually wondering, why did I actually multiply this nicely motivated term with some pixel values, right? So I'm going to answer why they do that. So let's say we take their definition of integrated gradient, x prime I minus xi times this directional sum of gradients. Then we can actually sum over the pixel-wise contributions given by this formula. And that's going to give me sum over I, x prime I minus xi times the inner product between ei and the integral of all these gradients along the curve. And that gives me this formula, which is the gradient along the curve into the direction of the where the curve is parameterized. So you're kind of taking the gradient into the direction through the direction of x prime minus x, and then you're averaging out the gradient along the curve. Okay, and this is actually a very nice term that has a strong connection with the fundamental theorem of integrals, which is a generalization of fundamental theorem of integrals. Well, actually, line integrals. Yeah, line integrals is a special case of, well, generalization of the actual fundamental theorem of integrals, which is saying if you integrate something, then integrate gradient of something, then that's the same thing as taking the difference between the boundary terms of the original function. Okay. And that takes the form of the following in the line integrals. So if you are taking the integral between a and b points for a curve in space parameterized by r, and let's say you're taking the integral of the directional derivatives along the curve for some function phi, then the result is the difference in the boundary values of this phi function. Okay, and here we can plug in f or phi, and the curve as a straight line that we had before, and then we're going to recover this function, this equation here. So if we sum over all the average over all the directional derivatives along this straight line, then that's going to give us the difference in the function value from fx to f of x prime. Okay, so in other words, if you sum up all the pixel-wise contribution of integrated gradients, then eventually what you're going to get is the difference between the function value for the final point and the initial point. And this is a case, this is an instance of something called completeness axiom for attribution method, which is saying if you sum up all the contributions for every feature in your input, that should actually give you the final output. So for example, let's say the x was a black image, let's say, and x prime was your input image. So your pixel-wise contribution, the sum of your pixel-wise contribution should be the difference in the activation from the prediction of the black image and the prediction for your image of interest. Okay. So here we are kind of introducing a notion of a baseline image, or an image without any information, right? And we are kind of measuring what kind of additional information we are adding per pixel on top of this baseline image. So these are the results of integrated gradients. You have an original image, and here it's nice that they actually mention what's the class here. So it's the camera, and the score is very high, which is good. And integrated gradients are giving us some regions around the camera, which is good. But they are kind of bashing gradients here, right? Because they're not giving us the right focus. The same goes for fireboats. It looks like they're focusing a lot on those fountain-like water splashes. Yeah, but the gradients are kind of not very much focused. So here they usually use a black image as a baseline, but there's a key downside of using that, because if you use black pixels as a baseline image, then by definition the contribution of any black pixel is 0, because there's a term that that multiplies x prime minus x at the front. So if your baseline is 0 and your actual image also has a 0 pixel, black pixel, then the contribution of that pixel is automatically 0. Okay, but does that make sense for, let's say, this black camera? Because those black pixels in the camera are also contributing to the final decision for sure, right? So the question is, what is the right value for encoding missing features for images, for example? Okay, so let's keep that in mind and probably move on. So there are like two extremes of measuring contribution in this domain. So one extreme is you are making very local changes in your input and then measuring the response of your network. Okay. And the other case, we are measuring those counterfactual responses by turning off some of the feature entirely. And by turning off, we are kind of have a connotation of we know what's the missing value, what's the baseline value for each feature. Okay. So from this perspective, we have different methods in the spectrum. So in the leftmost local perturbations, we have input gradients, but then we are slowly going more and more global by going considering more broader regions, as in smooth grad and then integrated gradients, and then we are going to look into those additional methods, which are actually turning off some of the features from the network and see the response. Okay. The nice thing here is that for linear models, there's no distinction between local and global. Okay. Because let's say, what is the gradient of this whole function with respect to phi I, right? That's exactly going to be Ci, right? So your local change of your local linear model will exactly reflect what's going to happen in the global scale as well. So this spectrum collapses into single point for linear models, and you don't have any distinction of these different methods for linear case. So yeah, in other words, you're always trying to kind of turn some complex non-linear stuff into some linear thing and try to understand this linear thing instead. This is probably one exception to that rule, which is doing this stupid thing, right, that I mentioned before, which is to compute this forward path several times. Yeah, I call it Zintracht et al. Because their method, they also have their method name, but it's less well known. But I'm still including this one because I think this is reflecting the actual notion of counterfactual very well. Okay, so what they do, they measure the missingness by imputation. What I mean by that is this is the quantity that we are interested in, right? What is going to be the response of the network when we remove pixel I, let's say, right? This backward slash I means an image without pixel I or feature I. And this can be written as some of our different possibilities for this missing pixel xi, where you're considering the probability of class C for different cases of xi, where the xi is kind of taken from the distribution of in-painting. So given all the surrounding pixels, what is the likely value of this missing pixel, right? So once we have this kind of model that fills in the missing information based on the surrounding pixels, we can average over multiple possibilities for this pixel value. And yeah, and you're going to have kind of function output for those different cases, and you average over them. And this is kind of expressed in this nice expectation formulation. And once we have this this value here, what we can do is to compare the responses before and after removing this pixel, okay? And that's going to give us this score here at the bottom. Well, here we're using log odd term, which they say is well-founded. But to be honest, I think you can use any difference here. Yeah, this is very expensive. And this is the results. And I think this is probably the most right solution, but the most tedious and most computationally heavy solution. So the red here means that pixel or that sliding window was contributing a lot to the final decision. And blue means it was negatively contributing to the final decision. Yeah, it looks very hard to interpret because, you know, like, let's say for GoogleNet, we are actually not seeing much contribution from the inner part of this balloon for the prediction. I guess the class was this balloon, right? So it's kind of hard for me to say. Yeah, but also maybe this is the true contribution of each pixel to the network prediction. So it's hard to say this is right or wrong. This is just what the method gives us. And we're going to talk about different ways to measure whether this is giving us the right prediction or not, right explanation or not later on. Yes?
What's it the common choice of the independent model?
Ah, right. So here they used a very simple method for in-painting. I think they used mixture of Gaussian, yeah, in the pixel space. But you can also use diffusion models for doing this. And then that's going to take years to compute this single image. So there is a trade-off between computational complexity and the quality that you're going to get. But yeah, I think anyways, this method is way too complex to be practical. Anyways. Okay. And right, so they are also comparing against this input gradient. It's a very easy baseline to beat. Yeah, the strong pro is that this is global counterfactual computation. So it's kind of true by definition, the score maps. But of course, it depends a lot on the in-painter. Yeah. Now let's talk about something that's a little bit more realistic. It's called line. It's been a very popular method for explainability community for 5 years, 5+ years. The strategy is to train a surrogate model, which is explainable by definition. That is, you train a sparse linear model that is close to your function values around the test point of interest, test input of interest. So here the F is the original model, and G is the surrogate model, where G is now a sparse linear model. And this phi x is kind of encoding the information of where is x in the space, input space, because we only want F and G to be similar around this input value x. And this omega of G is measuring the complexity of G. So this is the sparsity term for the linear model G. So to give you a bit more explanation into the terms. So this is the general formulation, of course, right? And your G looks like this, a linear model, WG and Z. So there's they're using X and Z in sort of an interchangeable way. I'm not sure if I can say that, but the point of using Z here is that instead of using pixels, which are X, they're actually using superpixels, which is a grouping of pixels. So to make a distinction between X and Z, they use both of them in formulations. But you can, for the sake of just understanding this equation, you can just treat X and Z as equal terms. Okay. So G is now linear with respect to X. And omega of G is measuring, is giving you infinite penalty when your number of non-zero weights are greater than K. So this zero norm is counting the number of non-zero elements in your vector. So that means whatever solution you have for G, it should be smaller than, it should have weights, number of weights smaller than or equal to K. Okay, and now the loss function looks like this. It's an L to loss function for the function outputs. So for Z and Z prime, the output of X, output of F, and output of G should be similar, right? Because this is L to loss. Where the weight is given by this phi X of Z, which is kind of measuring the radial distance from X. So what this is basically telling us is that F and G should be very close to each other around the point X. Okay. To explain all these terms, that's going to be very tedious. So I can just tell you that pi X of Z is just a term for making sure that the L to loss between F and G is only applied to points that are close to X. So this term makes sure that you train a linear model around this point of interest X. And that's going to be a linear model that's kind of respecting the local local changes of F. So it's like taking a gradient, but it's a sparser gradient than before, because you have the sparsity constraint as well. Okay, so once you train this kind of linear model on top of the superpixel features, then you can find out which superpixel is contributing the most to the prediction of certain class. So the superpixel that's contributing the most to electric guitar corresponds to this one, acoustic guitar to this one. Well, actually the electric guitar was wrong, right? But still, you can see why the model could have thought of this as an electric guitar, right? If they are focusing more on the more on this part of the guitar than the more discriminative part of the guitar. And yeah, you can also explain Labrador based on this superpixel. So now we can see that the results are more interpretable, and yeah, and but then this is actually making a huge approximation of the original model, because you're fitting a sparse linear model, which is very different from neural network. Okay, and the other con here is that your reference is assumed to be a gray image. Well, gray image is another representation of zeroness of the value, because when you input when you give an input to a neural network, you typically do mean subtraction and basically centralization of your inputs. So what is 0 actually as an input to a neural network is usually gray image, gray pixels. So here gray also means 0 pixel value in many cases. Okay, sure.
So can you sort of pinpoint where in the formulas it's actually written that we treat the reference as a gray image?
So the formulation does not say that, but yeah, the formulation doesn't say that. So it's a sparse linear model. So yeah, the sparsity is only with respect to W actually. Yeah. So W is either 0 or some positive value. Many of them will be 0, but that could be any value. But in their case, what they encode as a missing information is by turning Z prime here as 0. And yeah, I think this is popular choice for linear models, because for linear models, you can just turn one of the features into 0, and that also has an intuitive meaning. That feature is not contributing anything to the sum. Okay. Yeah. And then let's go to the Shapley values. But maybe let's take a short break for 5 minutes and then come back. Okay, so let's get started again. So we can jump to this famous Shapley values. Right, so Shapley values. This is a technique for understanding a black box system that takes an input and gives you an output. And the input is typically assumed to be in the form of zeros and ones, discrete values. And the output is a value in real number. So in a sense, your input is kind of a subset of a given set, right? Where zeros and ones are kind of indicating the membership to this subset for each element in the original set. So Shapley values takes binary inputs. That means turning on and turning off, depending on whether it's 1 or 0. And you can simply define your Shapley value to be this quantity here. So I'm going to explain what each term here means. So phi f and x of I means the contribution of feature I to the prediction of f of x. Okay, and x has features that runs from 1 to size of x. Okay, so the size of x is kind of indicating the number of features in the input, and I is the index for the feature index. And you're taking the expectation over different subsets of x. Z is a subset of x, where Z should actually include I, right? This feature of interest. And you're taking the difference between, it's kind of a subset set function version of gradient, because you're taking the difference between when I is taken and I is not taken, right? So in a sense, you're kind of taking the gradient at Z with respect to this feature I. So at every kind of set value, you're taking the influence of adding this feature value. And then you take the mean over the length of x. Okay. So for example, and Z is, of course, taking the subset of x, right? So if x is taking these two elements, then one valid sample of Z is this, for example, taking only this element here. Okay, so you're kind of taking the average contribution of I in all kinds of cases, right? That's kind of inside the original input X. Yeah. And the expectation here is not actually uniform across all possible Zs. That is a subset of X. But actually, there's a two-stage in taking the expectation here. So first, we sample uniformly from 0 to X, right? Well, it can't actually be 0 because Z should include I, right? So it's running from 1 here to the number of samples, number of features in X. And after that, you're sampling subset Z of size M containing feature I with equal probabilities. So not every subset has the same probability of being picked up here, okay? And probably subsets with smaller sizes are much more likely to be picked up than subsets of larger sizes. And by doing that, we can compute this coefficient here, right? So you can turn this expectation into summation, right? By providing the probability for each Z to be picked up. And actually the probability for a subset Z to be picked up out of X is given by this formula. This formula means it's a N choose C notation. Probably, I'm not sure if you're also familiar with this notation, but this is not a matrix. This is a single number. That's telling you the all possible cases of choosing this Z size -1 out of X size -1 possibilities. Okay, so if you write things down in factorials, then you get something like this eventually, where this 1/x term is taken inside the summation. Okay, so intuitively, why this number, right? This is because the total number of possibilities for choosing the set of size Z containing I inside the set X is equal to the number of cases where you need to choose all the elements apart from Z, right? So that's why you're taking the number of samples Z -1. 1 here means you're taking out I here. And the candidates to choose from is the whole set X minus I, right? So you also have this X minus I term in the upper side. Right, and then you have uniform probability. So you're just taking inverse of that as your probability, okay? And then you have this famous formula from Shapley values. And intuitively, what this is encoding is something like this for images. So let's say your eye is indicating the frontal face region of your cat, right? So you have all different instances of your input image with the cat's face turned on, but with randomly other features that are randomly turned off, right? So you average through all these cases, the function response for all these cases. And then you'll also have this case when you turn off your cat's face, but you're also randomly turning off any other part of the input image at the same time. And you take the average difference between these cases and the cases on the right. That's going to be your Shapley values. And the nice thing actually about Shapley values is that they also satisfy the completeness axiom as well. If you sum over all the Shapley values for the feature index I, then what you're going to get is the difference between the final function value for your input of interest X minus when X was 0, okay? So here again, 0 means special missing information input. And this is very similar to integrated gradients, right? Because for integrated gradients as well, when we sum over all the contributions from every pixel, then what we get is eventually f of x minus f of 0, right? So we have the same results here. And by the way, proof of this is quite interesting. So if you're interested in proving that, then you can kind of plug in this this formulation, and you can also do it by yourself, maybe. Yeah, it was a fun exercise for me. So, and the other nice property of Shapley values is the strong monotonicity property. It's not very important, but I introduced this concept here because I wish to kind of argue that Shapley values are some sort of special way of measuring contribution. It's the only way to measure contribution that's satisfying this strong monotonicity, right? So that's why I'm kind of bringing this up based on the previous studies. So to explain what this strong monotonicity means, let's say there's a two function, f and f prime, and there's an input x and feature I. Then let's say the following holds. The function value of fx minus the same function value when I is taken out is always smaller than the same quantity for f prime. So this kind of means that the contribution of I is always greater for f prime than f, okay? So contribution of I is more stronger for f prime. If that happens, then the contribution measure for f prime, the Shapley value for f prime for feature I should be higher than the contribution Shapley value for feature I for f. Okay, so if a function is kind of valuing this pixel a lot, right, then that should be kind of reflected in the Shapley value as well. And this holds, and the converse is also kind of true, meaning that the only way for some attribution value, phi, to satisfy both the strong monotonicity and the completeness axiom is to take the Shapley values. So if you wish to have this and this, then this is the right equation that you're looking for. So that's one of the theorems from some game theory literature that I put here. Yes?
Why do we want these two properties at all? Why are they useful?
Yeah, that's a good question.
I see that, for example, strong monotonicity, it makes intuitive sense, but I don't really see why you would want that at all.
Yeah, to be honest, I don't also find a strong reason why this is sort of the holy grail for anything, right? And also, those papers do not also give a strong reason why this is strongly connected to any real-world properties and so on. And typically when, so these are kind of explanation works that are built upon axiomatic foundings, they say, where they introduce some natural requirements like, okay, it should be strongly monotonic and it should be completeness, it should have completeness and so on. And then they eventually say, okay, actually any method that is satisfying all these axioms is only ours, right? But sometimes they take different set of axioms and results in completely different formulation. For example, this integrated gradients is also a unique formulation that's satisfying a different set of axioms. Okay, so these are different methods, right? So depending on what's your kind of selection of your word, like preferences in your word, you're going to get different attribution values. So I don't really think these are like absolute necessity and so on. It's more like a great way to kind of connect your possible real world need into an actual explanation method that you probably wish to have. But yeah, sure.
So the strong monotonicity is really only true for this exact formulation and no other convex combination of those differences or something like that. All of that wouldn't work. It would only work in this specific. Yes.
Yeah, that's what they say. Yeah. These specific coefficients is the only solution. Yes.
One question, is there a way to expand this so that we don't have only binary inputs, but just general vector values?
Oh, okay. You mean instead of binary, what about extending this to?
Directly now X is the only binary vector. It seems limited. Maybe I'm confused. I don't know.
Yes. Yeah, that's true. Yeah. But actually, for images, you can actually encode zeros and ones as whether turning on or off your superpixel. Okay, so actually for line, I need to double check, but for line, their input Z was actually a feature output for that superpixel region. Okay, so then they had a natural notion of kind of continuous feature in their case. But actually, if you wish to use Shapley values, you're treating the binary values as whether you turn on or off your superpixel. Okay.
When we choose those superpixels, then in which we compare those Shapley values.
We can use any superpixel algorithm, for example. There are many different ways of doing that, but I guess your question is something different.
No, I think that's it.
Okay.
If we just consider every superpixel, that's 2 to the
Yeah.
power of 500 pixels, and that sounds like an awful lot of computation.
All right, yeah. So I didn't mention here, but you can also do approximation by just sampling Z at random, and hopefully we don't have to traverse through all those exponential number of subsets here. So that's typically what they do when they try to compute this. Yeah. So yeah, there was a defense on defense for Shapley values, why they are so special. If they wish to have these nice properties, then this is the only solution they need to take. And one common theme here is how to define a missing value, right? For integrated gradients, we use 0 pixels, black pixels. Sintgraf et al., they used imputation in painting as missing features, and then they marginalized it out. I think this is kind of the most right way of doing it, except that this in-painting model can itself be right, because language models are also in-painting models in a sense. And to train this right, they had to train a huge model. The same goes for diffusion-based in-painting models as well. They are training a huge model to make it realistic. So it's not as easy as it sounds. Line uses mean values, the gray pixels. Shapley also has used mean values as missing features. But again, yeah, I'm kind of repeating here, but those missing, if you fix a missing value, then that color may be used somewhere else for encoding some information, like black car or gray building, right? So what people also tried was saying, instead of colors, encoding missingness in colors, you can probably blur it. Blurring can probably actually kill information instead of adding more information. So in this case, the prediction was flute, right? But suddenly when you blur out this region corresponding to flute body, your flute score goes all the way down to this, right? It's still kind of hard to believe because you still know that this person is playing flute. But yeah, that's one motivating example they had. And in this case, the learned mask is exactly the region where things are blurred out. Okay. And to give you an idea of how one can train such a system, such a mask per image, based on the mask you're doing blurring, right? So the objective function for the mask looks like this. So you're looking for M star among, yeah, actually this has to be a binary mask, right? So this is binary mask. Yeah, what I'm not sure here is whether this is a range between 0 and 1 or a set of zeros and ones. I think it should be something closer to a set of just 0 and 1, but I think for the optimization purpose, they just relaxed it to the range between 0 and 1. So yeah, it's a binary mask, a semi-binary mask within 0 and 1. And you have two terms. So the first term is measuring the area of the erased area. Okay, so M means M equals to 1 means you're still showing that part of the image. So measuring the L1 of 1 minus M means the size of the blocked area. And there's a classification term. So this large phi of X node and M means you're blurring the part of the image that corresponds to 1 minus M. Okay. So X node is the original image. And the important thing is that this formulation here is fully differentiable with respect to M, right? And therefore, you can train this whole system with gradient descent. Okay. And that's sort of the intuition behind how one can train such a mask. And they have this kind of interesting example of how this could be used. They say for detecting if there's a chocolate sauce or not, actually what the model is looking more at is the spoon rather than the actual sauce. Right, so you can also see here that by removing the chocolate with blurring, you do not see much drop in accuracy from 61. It's not accuracy, it's confidence level. But actually by removing the spoon pixels, you do see quite some drop in confidence value, right? So that means your model has been looking at the spoon rather than the actual sauce for making prediction. So the argument is by using this method, you can find those kind of spurious correlations and fix it. Yes.
The heat map in the first image shows the kind of amount of drop in the confidence score. Right? What does it show?
So it's the mask that you computed from the previous optimization, right? Yeah. And score changes, yeah. So again, we were talking about two different ways of measuring contribution. So yeah, and let's talk a little bit more about the choice of features here for visual models taking images and input, right? We are talking about superpixels. Lime uses superpixels, for example. And I said superpixel is some grouping of pixels, but actually there has been a lot of improvements in superpixel technology until a few years ago, but I think nowadays there are not as many people looking into superpixel technology anymore. But yeah, superpixels are kind of grouping of pixels without any knowledge of what's the final task and so on. But it's only looking at the color and edge information in the image to kind of group things that are very confidently belonging to the same instance of an object. Okay. It's kind of it's still kind of treated as a pixel, therefore, but these are coarser than raw pixels, and therefore you're kind of reducing the number of features to deal with. But now we talk about going beyond those low-level features into more higher-level human understandable features. Okay, so the work is called TCAV, Testing with Concept Activation Vectors by Bean Kim, and this has attracted a lot of attention. I think this method was also talked about in one of those Google hosted events, annual events, and this has got a lot of attention. So they complained first about input gradients again, right? Because if you look at the input gradients, you do not have any information about where's the important object for prediction and so on. There's no way we can kind of read this kind of map. Instead, what we really would like to ask is more semantic. For example, for predicting cache machine, is the model more looking at the cache machine itself, or the person, or the glasses, or paper? So these are like concepts that are expressed in human language, but not really expressed in terms of these input gradients in the pixel levels. Also goes the same for this gender bias in classifiers. So the question here is, was the gender concept more important to predicting there's a doctor or some other features, right? And instead of relying on gradients or pixel-wise or super pixel-wise attributions, if there's a way to attribute directly to the human understandable concepts like woman versus not woman, that'd be great. So yet another example that's going to be a running example for this these nice slides. By the way, the slides are from this TCAV authors for ICML presentation. So the talk is also quite great. So if you're interested, you can just go and also watch the talk. Now the running example is the stripe concept for the prediction of zebra. Okay. And of course, this striped concept is something that is not expressed in terms of superpixels or local kind of pixel-wise features. It's something that's kind of globally encoded in the whole image. Okay, so how do we attribute back to these higher level concepts? So let's say we have a neural network like this one, and we pick one of the intermediate layers with dimension m, right? And what we do is we prepare a set of examples actually for positive classes and negative classes. Well, actually, we only need the positive classes for the concept striped. Okay, so the above images are the striped concept images containing stripe, and the below is any random image. Okay. And afterwards, what we do is we feed those samples into the network and take a look at the features in the intermediate layer that we have that we had in mind, right? And then train a linear classifier on top of this intermediate layer for this concept. Okay, so now you're turning your model into having an additional function of being able to tell if a given input has some concept or not. Okay. And therefore, now, okay, so yeah, I wish there's also a figure here, but now what you're doing here is that you take the derivative of the final prediction, PZ, given with respect to the concept vector, actually. Okay. So here you give an input to the network, right? Here X, and then you pass it all the way through the network and get the prediction. And from the prediction we can backpropagate, right? But while backpropagating, we also compute the score with respect to this learned decision boundary in the middle. Okay. And that's going to give us the gradient with respect to this decision boundary for stripedness. And that's exactly the score that that we were looking for. How much of the stripedness concept contributed for prediction of this particular sample for a zebra? I hope it's clear. And what they also measure on top of that is they compute the mean of those contributions, the gradients. No. They compute whether this contribution is positive for all the instances in the data set for zebra. Okay. And then what that's going to tell us is whether striped concept was important for the prediction of zebra. So in a sense, you can kind of turn your local, this instance-specific analysis of whether stripedness is important for the prediction into more global one by saying for zebra class in general, this stripe is very important. Okay. Yeah, so here are some examples of using TCAP. For predicting fire engine, they looked at whether the color of the car was important. And it turns out that being red was contributing a lot to the prediction of fire engine. And being green also contributes a lot. So that also shows us a strong bias towards countries in the data set represented in the data set, having red and green as the color of the fire engine. Ping pong ball also has a strong bias towards East Asian, African ethnicity for the players. Rugby ball, African, Caucasian, right? So from this kind of analysis, we can more easily see what kind of features is the model looking at for making predictions, right? You can also do the same thing for medical image analysis. For example, the TCAP score here is high for those three features, which are indicated by doctors as an accurate cause for your prediction. But in this case, the prediction was depending also on this HMA feature, which the doctors say is not a good feature to look at. So with this kind of technology, we can more streamline the interaction between humans and computers for making predictions. Okay. So that was a quick kind of introduction to TCAP, and yeah, let's look back on the methods a bit. So as I said, explanation is about linearizing models in some way. So this is what input gradient is doing, right? So instead of looking at the prediction f of y, we are looking at the prediction of f of x, which is close to y, and then there's a linear term on top of that. Okay, so input gradient is kind of looking at a small perturbation around this test sample of interest, f of x. Lime is doing this more obviously by turning your model into a sparse linear model and trying to fit it to the original model. Integrated gradients is also turning your model into a linear model around the baseline. So now your model becomes your baseline plus the sum of the contribution from each pixel, which is measured by this formulation. And you note that this is exactly linear, because you're summing over the contributions from each I. And then there's sharp, and this is also a linear function because you're also summing over contributions depending on these coefficients. Yes. Right. So in terms of like okay, so f of x in this case, as I said, x is composed of individual features, right? So this phi x fx of I is individual contribution from each pixel, right? So you're summing them over different pixels, and that gives you the final prediction. So in a sense, by turning on or off your pixels, it's regulating whether you are including this contribution to the final prediction or not. And so in that sense, you can think of this as also a linear model of your linear approximation of your model. Okay. So conceptually, what you can draw out of this is one way to linearize your model is by turning your complicated F model into an interpretable F prime model around the local neighborhood of your input X. Okay, so this is very easy. You can do it through taking gradients and so on. Or doing any of the previous methods, right? These are all local methods. Around X, you can explain everything nicely, interpretable way. But we also looked at TCAP, which is doing something like this. So given an input space, it first maps your input into a space of interpretable features. And then based on the interpretable features, you're finally making some prediction. Okay. So instead of explaining everything in terms of the input features, in this case, you're getting help from the intermediate interpretable features, and you're only approximating the second part of the network through gradients. Okay. And therefore explain things in terms of interpretable features. And this is the case for TCAF, because you're taking the gradient with respect to the intermediate layer. Now we're going to look at the class of methods that are considering a model that looks like this. So the first part of the network is complicated, but at least the second part of the network is interpretable. It's kind of linear from the beginning. And therefore, we do not care about this first part, but the last part is kind of nice to deal with, and therefore we are just looking at them. Okay. These are class activation mappings, for example. So you have an input image, and you have a model, and you have a score map, and then there's global average pooling, and there's class label. And this is a typical convolutional neural network-based classification system, right? And at test time, instead of doing the global average pooling, you can also do thresholding. And then in that case, you're going to get foreground background mask as an explanation. Okay. So here you see that up to this point is very complicated using convolutional neural network, but afterwards it's just a linear model, just global average pooling. And therefore everything is highly interpretable, and you can kind of use the linearity here to study the score map very efficiently, like which pixel in the score map is contributing most to the final prediction, right? And here the key assumption is that the attribution to the pixels in the score map kind of corresponds to the attribution to the original pixels before the CNN. And that's a huge, huge leap of trust. But people also say CNNs are kind of preserving the localized information throughout the network, and therefore we just trust that, yeah, they're doing that. And so the explanation with respect to the score map also corresponds to the original image, okay? So that's a way to kind of go through, like linearize one part of the network and disregard the other part of the network confidently. And this is the original CAM formulation. I'm showing you this because I also wish to talk about how to fix the original CAM formulation into the identical formulation that is more computationally easier. So what they do first is they get this kind of convolutional feature map, and then they do global average pooling on top of that. That's going to give them a vector per image. So this blue part is average pooled into this single number here, red part into the red here, and so on, right? And after global average pooling, they do one linear layer to into the classes that you wish to predict. So for every class, you have a dedicated weight attached to every hidden dimension here, okay? And you get the final answer. And of course, you do softmax on top of that. And ideally, you also put negative log likelihood to train this whole model. So this is the training scheme. And then at test time, what you do is you take this intermediate feature map, F bar, again, and then you take those W values of your model for the class of interest, basically Australian Terrier. And then you sum over all these feature maps with the weights given by these Ws. And that's going to be your class activation mapping. Okay. So you're doing some kind of linear computations and softmax above, and then also doing some kind of linear computation for explanation. But I think a lot of people pointed to the fallacy here, which is that why do you do that, right? Why do you do linear computation here and also do the same kind of linear computation later on? Why can't you just take a look at a feature map, which is kind of here after doing the linear computation? So I'm going to explain what I mean by that. So this is how the training likelihood looks like. So you start from this feature map and then do average pooling and then do linear matrix multiplication. But here we note that this global average pooling and this linear multiplication can be swapped because both are linear operations. So in other words, you do linear matrix multiplication for W first, and then do global average pooling. It's the same thing. And now we define the results of this linear matrix multiplication as F of Y HW, where Y is now running through the classes. Okay. Yeah, this is possible, right? And then we can write this difficult formulation into a simpler one, where we simply do global average pooling into class-wise vector, and then do softmax. And now we have a simpler training formulation, and then we can also simplify the explanation algorithm, which is taking the matrix multiplication between W for the class of interest Y hat and the F bar. Well, actually, that's the same thing as just taking the Y hat value from this new feature map that we are considering, right? So instead of doing this kind of linear computation twice, you just do it first during training, and then at test time, you simply take the value corresponding to the ground truth class of interest. And that's going to give you the CAM score map right away. Okay. Right. But now, by doing this, you actually do need to modify the original model a little bit. Because now it was global average pooling and then fully connected layer. But now it's actually one-by-one convolutional net layer and then global average pooling. Because now you're dealing with, instead of vector, you're dealing with feature map. And you see, linear layer is doing the same thing as one-by-one convolution, right? Because you're applying the same matrix multiplication for every pixel in the feature map. And that is exactly one-by-one convolution. So in terms of code, it amounts to change a few parts in your model .py code. So instead of ResNet, you now have ResNet conv 1x1. So the left is the original model, original ResNet with original CAM formulation. So you have average pooling layer and then FC layer, right? But instead of doing that, you have convolutional layer, additional convolutional layer before average pooling, where the number of weights, number of inputs and outputs are kind of the same as the FC layer. So they actually contain the same number of parameters. And here you do average pooling and then flattening and then linear layer. But instead of doing that, you do convolution first and then average pooling. And now the last method here is about computing explanations. And the CAM formulation requires you to compute a very complicated way to pull out the weight from your model, and then take the weight corresponding to your output, and then unsqueeze, and then do the matrix multiplication. No, we don't need to do that. We just need to take the output of your convolutional layer, and then take the slice corresponding to your class of interest, and that's it. So in my opinion, the right side of CAM implementation is much simpler and much nicer. So I always use the right side. And whenever someone uses the left side, I say, why do you do it? Okay, so maybe we can stop here for today and continue the rest tomorrow, because we still have a lot for the CAM side. Okay, CAM is very important. So, all right, thank you, and see you next week.